All right, we're going to find the area of a region, area under the curve, above the x-axis, between the x-axis and that curve, or below the x-axis, between the x-axis and the curve. And we're going to use the limit process. It's a little bit of work, a lot of writing, and then later on we'll learn another notation, a quicker way of doing it. But now we're going old school, using limit process today. So taking what we learned yesterday, and we're going to have the definition, the area of a region in a plane, so area under a curve. Okay, let f be continuous and non-negative on the intervals or a to b, closed interval. The area of the region bound by the graph of f, the x-axis and the vertical lines a and b, can be defined by area equals the limit as n goes to infinity. That means number of partitions or number of sub-intervals goes to infinity of the sum of I equals 1 to n of f of c sub I. That means f of the x values that we come up with when we plug in 1, 2, 3, 4, 5, 6, all the way up to infinity, times delta x. So that would be the area of those rectangles. We're going to add infinitely many of them. And delta x, guys, can be defined as ending value minus beginning value divided by number of partitions. And we don't know the number. Well, we do. It's infinity. So, but we just use n. So this is how we're going to start our problems. We'll find the area of the region using the limit process. We're going to start our problems this way. We're going to figure out what our change in x is using b minus a over n. We're going to figure out what our c values, how to come up with our c values. We're going to substitute those c values into our function, and then we're going to rewrite the sigma using some properties from yesterday, and then we're going to let n go to infinity. We're going to analyze the powers top and bottom, go from there. Find the area of the region bound by the graph of f of x equals x squared, the x-axis between x equals 0 and x equals 2. Notice, this problem is different from the previous ones because it doesn't say use a left or right or mid or trap sum with a n partitions or n subintervals. It doesn't say any of that. It just says find the actual area under the curve. Okay? If they don't tell you the type of sum they want you to find, they don't tell you the number of partitions, we know it's the actual area, and we use the limit as n goes to infinity of the sum I equals 1 to n of f of c sub I. Remember, that's our height. What in the world just happened there? Times delta x. That's weird. Okay, remember, this is our height. This is our width. Okay, let's think about this. We're going to graph this just to analyze it a little bit. Okay, we have x squared. So if we go over 1, we go up 1. Go over 2, we go up 4. And so there's our graph of x squared from 0 to 2, right? We need to find the area under here. So our goal right now is to figure out what change in x is. Okay? Delta x is always going to be b minus a over n. And in this particular case, a is 0, b is 2. So delta x will be 2 minus 0 over n, which is just 2 over n. Mr. Bonley, why are we not substituting in for n? Because n is infinity, right? Infinite number of subpartitions. Okay, so we have delta x figured out. Now we need to figure out what c sub I is. Now, for us, and it's the easiest way, is to use the right-hand x value of the subintervals. Okay, so c sub I is the right-hand x value of each subinterval. Okay, so let's just do a random subinterval like right here. It's going to look like this, right? So how do we get to the right hand? Well, it's always going to be, c sub I is always going to be a plus b minus a over n times I. Always, always, always. So in this particular case, what does it look like? It's going to be our starting value, 0, plus, isn't b minus a over n? That's just delta x, right? That just gets us to the next subpartition, subinterval, okay? And that's where the I comes in, because the first subinterval gets you over here. Your change in x, 0 plus change in x. Well, then you multiply by 2 for your next term. That gets you over to this one, right? Multiply by 3 gets you over to the next one, okay? But they're infinitely small, 2 over ni then. So in this case, c sub I equals 2 over ni. So if we plug this delta x and a c sub I into our limit, we have the limit as n goes to infinity of the sum. And don't try and skip steps, guys. You have to write everything out all the time. Okay, f of, and for this particular situation, 2 over n times I. That's what we're going to substitute into the function, times delta x, which is 2 over n. We have our c sub I figured out. We have our delta x figured out. Plug your c sub I into the function. Well, the function is x squared, so now we have the limit as n goes to infinity of the sum, I equals 1 to n. We'll just plug 2 over ni every place you see an x, right? That's how we evaluate functions. So it'll be 2 over ni squared times 2 over n. This is the function evaluated at 2 over in. The function evaluated our c sub I value. What function? They told us, x squared. All right, now what did we learn yesterday? This is the index of summation I. We have this factor 2 over n, which we don't have to leave in here anymore. We can bring it out in front. We can put it in front of the sigma. We cannot put it in front of the limit because the limit is in terms of n. Okay, so next step, factor out what you can. So we can factor 2 over n out. Okay, and now we actually have to expand this so that we can try and get rid of the sigma notation using those properties we learned yesterday. Okay, so if we take the power of this, that'd be what? 4 over n squared times I squared, right? Do you guys notice we can bring something else out now too? We have 4 over n squared times I squared. Well, this is a factor, does not have I in it. Let's bring that out in front now. Okay, if we bring 4 over n squared, that would be 8 over n cubed now, wouldn't it? And I squared. Well, what do you know? We have this sigma reduced down to just I, just in terms of I squared specifically. And what is the sum from I equals 1 to n of I squared? What does that equal to? So 8 over n cubed times, because this is a product, right? What is this, guys? N, over 6. right? Now, we don't have a sigma anymore. That's awesome. That's our goal. We need to get to that spot. For now, we can analyze this limit. Okay? Now, here's the deal, guys. I don't want you multiplying this limit all the way out. I don't want you multiplying this all out. We don't need to. Why? Let's figure it out. Okay, n goes to infinity. What do? We analyze the power in top and bottom. Okay? If we did multiply this all out, you'd eventually have 8 times n times 2n, which would be what, 16n cubed? We'd have 16, well, let's do this better. Make this a little more formal. Okay, limit n goes to infinity. We'd eventually have like 16n cubed plus some residuals, right? We have some n squareds and some n's and some constants, right? But we know as n goes to infinity, those are not as important as our highest power. And the denominator, well, that's really easy, n cubed, okay? Now, this does not equal this, but I'm just writing it out right now so you guys can see what's happening. Same power, top and bottom. What does this limit equal? Ratio of coefficients, which is 16/6, which is then what, 8/3? Okay, and they want us to find the area under the curve, so we need units. They did not tell us what the units were, and of course, if it's on the coordinate plane, it's always going to be unit squared. Okay, there's a way we can check our work using a calculator. Get your calculators out. Let's see if I can do this without. Let's go to 9. Math 9, hit enter, and it brings up this goofy stuff right here. This is actually what we're going to get to pretty soon. Okay, that's called integral. Okay, so how do we enter in this integral to try and check our answer here? Well, what we just did is we found the integral. From right here, what we need to type in, we have antiderivative. Lower bound is 0. Upper bound is 2. Then we type in our function, x squared. And then we actually need to put dx also. Type that in your computer, or your calculator, basically computer. Type that in your calculator and see what you get. Do you get 8/3? You do? Obviously, it's going to give you a decimal approximation, right? Okay, 2.6 or whatever it is. Okay, so that's how we can check our work. Later, we're just going to be able to figure this out numerically. That's our next step in this chapter. Okay? Okay, find the area of the region bound by the graph of f of x equals x cubed and the x-axis between 0 and 1. These problems are not too bad if a is 0. A little more clunky if a is something else, because that creates a binomial that we have to substitute into the function. Okay? Start at the beginning again. I know this is the limit as n goes to infinity of the sum I equals 1 to n f of c sub I times delta x. We defined what delta x was. Again, that was b minus a over n. B is 1, a is 0, so 1 over n. Okay, c sub I, we defined as a plus, and I'm going to write this again, going delta xi. So that would be 0 plus 1 over n times I. Sometimes you'll see, if you watch other people do videos or other people work problems or other books, they put I in the numerator right away. I don't like to do that. And so our c sub I is just 1 over n times I. And the reason why I don't do that is because I know that this is going to get factored out eventually. Okay? Okay, set up our problem. Limit. N goes to infinity. The sum, I equals 1 to n. F of 1 over ni times delta x, which we came up as 1 over n. Mr. Bonley, is this delta x part always going to be factored out in front? Yeah. Let's do that. And while we're doing that, let's substitute c sub I into our function. Whoops, I forgot to move it. n times sum. Okay, f of 1 over ni. F is x cubed, so it'll be 1 over ni quantity cubed. Okay, distribute your power basically. Okay, sum equals 1 to n. So 1 cubed, n cubed, I cubed. So 1 over n cubed times I cubed. Now we're back to we have a product again. We can factor this out, make it a constant multiplier. Okay, if we move 1 over n cubed out, that'd be 1 over n to the fourth, right? And then the sum, I equals 1 to n. And I cubed. What in the world is I cubed? Say again? Like that? There's something else missing. Quantity squared up here, right? Okay, so we got it. So we have our sigma isolated into a form so that we can make a substitution. We have our substitution, no more sigma. Now we can just focus on finding the limit as n goes to infinity. Now I don't want you to do a whole bunch of work on this, obviously, right? I want you to use your critical thinking skills. If I had to multiply this all out, well, I'd have an n squared eventually, right? Times n squared, which would be n to the fourth power times 1, right? So if we have 1 n to the fourth power on top, what would you have on the bottom? 4 n to the fourth. So this limit would just be 1/4. So the area under the curve would be 1/4 unit squared. All right, I'm going to go back to, I'm going to open this one up first. See if I can do this. All right, we can find this, right? Plug in 0, 1, x cubed dx, right? Let's do this another way. There's another way to find this area, which is kind of more interesting. Let's go to y sub 1. Let's put x cubed in here. Let's go to your graph. And I'm going to change my window just so it looks better. I'm going to go, what, -2 to 2. And then at, let's just go -8 to 8 for fun. Look at the graph again. Okay. And honestly, we're 0 to 1, aren't we? Let's change the height again. Let's go, because 1 cubed is 1. I'm going to go -2 to 2, also on the height. All right, that's better. Now, go to calculate. Okay. Look at number 7. Go to number 7. It's going to say lower limit. What's our a value? 0. Hit enter. What's our upper value? 1. Hit 1. Hit enter. Look at that. It shaded in for us too. It actually showed the area under the curve. This area is positive, right? Because it's above the curve, isn't it? Okay. Let's see what the calculator does if we go from like -1 to 0. Let's do that real quick. Let's go calculate 7. Lower limit. Let's do -1 this time. Let's do 0. It shades this region now. And the area is underneath the curve, underneath the x-axis, I should say. It's symmetric about this one, right? So it's -0.25, so -1/4. What would the area be if I went from -1 to +1? 0, because you'd have the negative area plus the positive area be 0. Okay? All right, last problem. Let's see if I can switch over now. See if we outsmarted this program. Ha! Got you. I might have to do that now is just open up two of these programs if I need to use calculator, go back to one. I'm going to try that, see if it works. All right. Now, how do we make these problems more difficult? It just makes the algebra a little more difficult by adding a couple terms into our function. And then also by not starting at 0. Okay? We could use our technology, type this in a calculator, and find the area instantaneously, right? But what they do in the AP test is they will give us they might give us, let's see, right here. They might give us this, and they'll say, what's the function? What's the A value? What's the B value? And so we have to go backwards to be able to figure this stuff out. Okay, that's why we do this whole process. And then I'll give you guys some problems where we go backwards and figure out the functions. We practice it, don't worry. Okay, how do we find the area of the region? Using the limit process. Well, we go limit n goes to infinity of the sum I equals 1 to n f of c sub I times delta x. Okay, delta x, b minus a over n, 2 minus 1 over n. It should be 1 over n. Okay, c sub I equals a plus delta xi. In this case would be 1 plus 1 over ni. Go back to our limit now. Limit n goes to infinity. The sum of I equals 1 to n f of 1 plus 1 over ni times 1 over n. They like to give you guys this problem a lot of times and ask what's the function and what's the bounds and stuff. Then they'll say, which one of these is equivalent to this? Well, it's going to be 1 to 2 of 4 minus x squared dx, right? So that's where we're going to be going with this. They'll ask some questions like that. Keep going. Limit. Okay, I'm going to put my 1 over n in front. Sum I equals 1 to n. F of this business. Okay, well, that's going to be 4 minus this garbage squared. 1 plus 1 over ni squared. Okay, again, now the algebra is just more difficult. That's it. All right, well, we're going to have to use some muscle now. So limit n goes to infinity, 1 over n, sum I equals 1 to n, 4 minus parentheses. Now let's square this binomial. That'll be 1 plus 1 times 1 over ni times 2. So that'll be 2 over ni plus this quantity squared. So 1 over n squared I squared. Use the appropriate amount of parentheses and brackets to keep everything organized. Okay, limit n goes to infinity. And notice it kind of escalates in a hurry. Once you have a binomial in there, you're evaluating your function, a little more difficult. Sum I equals 1 to n. Okay, that's going to be 4 minus 1, then minus this, so 3 minus 2 over ni minus 1 over n squared I squared. All right, now we have to use our properties and break this up. Okay, limit n goes to infinity, 1 over n. Okay, we can basically distribute our sigma through the sum or difference. So that'll be what? The sum I equals 1 to n of 3 minus the sum. Okay, now if I put this sum here, that means 2n can go out as a constant multiplier and I can stay as the argument of sigma. Let's do that. Save ourselves one step of writing at least. Minus. Same thing over here. 1 over n squared can be moved in front of the sigma. I squared. There we go. Now we're to a point where we can make our substitutions and get rid of those sigmas. Limit n goes to infinity. 1 over n. Okay. The sum from I equals 1 to n of 3. 3n. Minus 2 over n times, well, what was I? Is that n times n plus 1 over 2? Check me on that one. All right, minus 1 over n squared. Okay, I squared is n times n plus 1 times 2n plus 1. This is the one where people get wrong because they forget to multiply by 2 when they're figuring out their limit. And that's all over 6, I believe, right? Okay, next step, what I do is I distribute my 1 over n. And notice what's going to happen. It's going to cancel that n. It's going to cancel this n. Okay, so on and so forth. So limit n goes to infinity. If you don't feel comfortable canceling, just write it as 3 over n or 3n over n minus. Okay, it's going to be 2n, n plus 1 over 2n squared, right? If we multiply by n in the denominator, minus n times n plus 1 times 2n plus 1 all over 6n cubed. A lot of writing. Okay, I think we're in a good position to find this limit. And remember, finding the limit of a sum or a difference is just adding up those individual limits, right? Okay, let's let n go into infinity of the first term, and we get 3, I believe, minus. Okay, we'll have 2n squared eventually divided by 2n squared. Ratio of those coefficients is 1, minus. Okay, let's see here. We got n times 2n, so it'll be 2n cubed over 6n cubed. Okay, so power is the same, so that'll be 1/3. 3 minus 1 is 2. That'd be what, 6/3? So 5/3? Finally. I don't think this stuff is too bad. There is a definite process, and it is a little bit, there is a little bit of algebra rigor in here. Just got to mind what you're doing, make your substitutions correctly, and then take your limits correctly. Okay? And if you type this in your calculator, obviously you're going to go, what was it, 1 to 2 of 4 minus x squared. Make sure this is in the parentheses if there is any, and then dx. And if you graphed it under y sub 1, it'll show you shading the area. Or if you type this in Math 9 from your home screen, it should give you, what, 1.66666. Okay? Questions on this at all? Mr. Bonley, is this an overestimate, underestimate, or what? This is the actual area under the curve.